Okay. In simulated version, we have Hatem Elshatlawy, who's going to be talking about observers and Ruliology.
Wonderful. So good afternoon, everyone. Unfortunately, I couldn't join you in person today due to a sudden illness that struck me yesterday and sadly persisted into this morning as well. However, I'm grateful for the chance to share my presentation through Zoom, and I hope you find it engaging and informative. Well, first of all, thanks to Dean for actually organizing such a wonderful conference, and thanks everyone for being part of that. So in my talk today, I'll be diving into the realm of computation with a particular focus on the central role that observers play. The insights I'll be sharing with you today are mostly based on a recent preprint in collaboration with Dean Reckles and Xerxes as well. You can also find the paper on arXiv for sure. All right, so before talking about observers, I think it makes sense to tell you what Ruliology is. So Ruliology is a term that is coined by Wolfram, which actually means the pure basic science of what simple rules do and how different rules can lead to diverse and complex behavior. So if one sets up a particular system to follow a particular set of rules, what will the system do? Or to say it in another way, how do all those simple rules, how do all simple programs out there in the computational universe of possible programs behave? So I'll try to give you a brief overview of the Wolfram model, focusing more on its core concepts and conceptual issues than formal details, while emphasizing the role of observers within the model. So the Wolfram model proposes a computational universe constructed using rewriting systems and evolution rules. The model originates from the idea that the basic building blocks of the universe are fundamentally discrete and are governed by computational rules. A key objective of the physics project is to seek a formulation of fundamental physics within the framework of rewriting systems. Before discussing the details so much, I maybe want to say a few things about the backstory of the project, a little bit of the history. As maybe some of you know, that the physics project is actually just some developed seeds of the NCAS, a new kind of science. And when Stephen was writing a new kind of science, studying the computational paradigm and the computational universe of simple programs, he identified two key empirical observations. The first observation is that theoretical science is often based on mathematical models, but there is no reason to believe that only the kinds of rules studied within the context of human mathematics should somehow be the end of the story. Since computer programs effectively implement general sets of rules, why not use those as a more general basis for doing theoretical science? And the second observation is that very often simple programs do complex stuff. It doesn't really matter whether they are elementary cellular automata, Turing machines, combinators, substitution systems, stack systems, you name it. It doesn't really matter whether they are based on continuous mathematics, based on constraints, based on numbers, strings, expressions, graphs, or more general kinds of objects. It doesn't also matter whether you start from random or simple initial conditions, operate deterministically or stochastically, operate in 1, 2, 3, or more dimensions. One always sees the same kinds of complex behavior. And this is not complexity that's coming from the external environment, or that has been encoded in the details of the initial conditions of the system, as in chaos theory. Rather, such systems are intrinsic generators of complexity. So back in 2002, Wolfram did propose this radical conception of the scientific method, where in effect, rather than starting from the phenomena, then drilling down, you start from the very basic parameters, or a class of possible models, and building up using computation to explicitly calculate what a particular model is going to do, and then make connections between the semantic outcome of the model and the actual phenomena observed in nature. And so in a sense, the physics project is a natural continuation of these ideas. We also know from NKS that pattern matching and substitution is a minimal model for almost everything. It's really the archetypical structure that underlies all computational, mathematical, and symbolic systems. And just to give you a few examples, a Turing machine is a discrete set of arrays. You have the head that goes over each cell, scans it. If it's a given sample, it will do something. In a cellular automata, the color of each cell would depend on its neighboring colors. Every time you see, let's say 2 plus 2 equals 4, means that every time you see 2 plus 2, you just replace it with a 4. Hence, pattern matching and substitution. That's the minimum model that we claim is a good model for many things. And now back to the Wolfram model itself for physics. As I said, it really originates from the idea that the basic building blocks of the universe are fundamentally discrete and are governed by computational rules. The Wolfram physics project may be thought as being the study of pre-physics. It really is a constructivist model by nature and seeks to formalize the fundamental structures of physics. And here we think of the evolution of this model as corresponding to a computation, where the system starts from an initial state, follows its rules, in effect carrying out a computation to generate a sequence of states. And just to give you an example, that's basically a directed hypergraph, and the elements could mean anything. We don't really care about the elements. All we care about is just the relations between elements to other elements, the connectivity between points to other points. And here one could also say that each directed hyperedge corresponds to an ordered, in this case, an ordered relation between abstract elements, allowing us to represent the hypergraph itself as a finite collection of such relations. And here we define a rewrite rule that basically says it's a transformation rule that could also be represented as a set substitution system. And that says if I have such a pattern, I'll just replace it with that. And then we apply this rewrite rule to this guy here, and we have such an evolution, as you can see. And after a few iterations, we get to this guy here, which is interesting how complexity can indeed arise from very simple rules and simple initial conditions. So at its core, the Wolfram model is just really a discrete space-time formalism in which the continuum structure of a manifold emerges as the largest scale limit of a discrete causal network. And the causal network is generated in a very natural and algorithmic way from diagrammatic rewriting rules. So we're ultimately trying to develop an explicitly computable constructivist foundations for physics based upon discrete space-time. Parallels to causal set theory, causal dynamical triangulation, spin networks, spin forms in loop quantum gravity, etc. Parallels also to constructivism and intuitionism in the foundations and philosophy of mathematics. And just as constructivism is all about giving explicit algorithms for constructing mathematical objects, the Wolfram model for physics is all about giving explicit computational processes for constructing physical objects, rather than reasoning abstractly like saying let M be a manifold, let S be a space-time, let H be a Hilbert space or whatever. Instead you say here's an algorithm or a computational procedure that builds me a manifold, a space-time, a Hilbert space. We also know from these programs that it is indeed very useful to think about space-time and the foundations of physics from discrete and computational terms. Because in traditional physics, we think of a space and time as something that is given. And on top of that, you throw stuff in, for example, matter, and then we hope that matter will interact and stuff happens, and that's how we view reality. But the first thing that one needs to answer, if one wants to do physics in a background independent way, where does space come from? What's the underlying structure of space? And one way to answer that is through the rewriting systems. So one could also say that at the lowest level, we have a machine code description of the universe, in which everything just consists of a network of atoms of space that's being continually updated. So yeah, multi-way systems and the concept of multi-computation. That's when it really gets interesting. So historically, I think one can identify 3 major paradigms that have dominated theoretical science, each of them leading to dramatic progress. The first one, originating in antiquity, one might call the structural paradigm. And its key idea is to think of things as being constructed from some kind of simple to describe elements, let's say geometrical elements, and then to use something like logical reasoning to work out what will happen with them. Then there is the mathematical paradigm, which just really rely on formulas to describe phenomena. And many would say that modern exact science was launched in the 1600s with the introduction of what we can call the mathematical paradigm. The idea that things can be described by mathematical equations and that their behavior can be determined by finding solutions to these equations. And I guess for hundreds of years, the mathematical paradigm was the state of the art in theoretical science. And of course, a lot of progress was made using it. And then starting in the early 1980s, there was some progress based on a new idea. The idea of using simple programs rather than mathematical equations as the basis for models of things in nature and elsewhere. And part of what this achieves is that to generalize beyond traditional mathematics. Because in the mathematical paradigm, one imagines having a mathematical equation and then separately somehow solving it. But if one has a program, one can imagine just directly taking it and running it to find out what it does. And this is the essence of the computational paradigm, to define a model using computational rules and then explicitly be able to run these to work out their consequences. So in the ordinary computational paradigm, the typical setup is to have a system that evolves in a series of steps by repeatedly applying some particular rule. Right? You have a system and you have a rule, you keep just evolving the system by applying that rule repeatedly. But for our models, for some rules, they are not deterministic. That is, multiple choices of substitutions are possible, which yield different results. Usually, in the ordinary computational paradigm, we just pick one possibility and ignore the rest. But the multi-way system explores all possible choices at once. And a key idea of our models is to really consider all those possible threads of history and to represent these in a single object that we call a multi-way graph. And consider, as an example, a system defined by the string rewrite rule A goes to BBB and BB goes to an A. This string substitution system. Starting from an A, the next state has to be BBB, right? That's the first rewrite rule. But now there are two possible ways to apply the rules. One generating AB and the other generating BA. And if we trace both possibilities, we get what we can call a multi-way system, whose behavior we can represent using a multi-way graph. And it's not really difficult to construct multi-way system models. There are multi-way Turing machines, there are multi-way systems based on rewriting not only strings, but also trees, graphs, hypergraphs, and there are multi-way systems based on numbers, and all kinds of multi-way systems. Here is a multi-way Turing machine, and that's a multi-way combinator system, and that's a multi-way system based on numbers. It's a binary tree structure that grows and divides, where you just apply S to every function. So combinatorically, a multi-way system is just simply a directed acyclic graph of states determined by abstract rewriting rules that inductively generate a potentially infinite multi-way evolution graph, together with a partial order on the rewrite rule applications determined by their causal structure. So one could say that at the core of the physics project is actually a new paradigm that goes beyond the computational one, a fourth paradigm that we call the multi-computational paradigm, that transcends physics and applies quite generally as the foundation for a new and broadly applicable methodology for making models in theoretical science. And it's really important to emphasize that the multi-computational paradigm is at its core not about particular histories, but about the evolution of all possible histories. And in most cases, it won't have things to say about particular histories, but instead, it will describe what an observer sampling the whole multi-computational process will perceive. All right, so now instead of looking at all possible ways a given rule can update these rewrite systems, imagine the structure of spaces created by applying all possible rules. Instead of just forming a multi-way graph in which we do all possible updates with a given rule, we form a Rulian multi-way graph in which we follow not only all possible updates, but also all possible rules. And that's an illustrative figure of Rulian multi-way graphs for Turing machines with different numbers of states and colors. So a multi-way system, again, just to recap, is applying a particular rule in all possible ways. But to get a Rulian multi-way system, you apply not only a rule in all possible ways, you apply all possible rules in all possible ways, somehow. That's when you get a Rulian multi-way graph. And this construction really allows us to think about the notion of Rulian space, the space of all possible rewriting rules of a given signature. By applying all possible rules and all possible updates, we get what we call the Ruliad, which is basically the result of following all possible computation rules in all possible ways. It's really the ultimate limit of all Rulian multi-way systems. And as such, it traces out the entangled consequences of progressively applying all possible computational rules. The concept here is to use not just all rules of a given form, but all possible rules, and to apply these rules to all possible initial conditions, and to run the rules for an infinite number of steps. Essentially, the Ruliology involves taking the infinite limits of all possible rules, all possible initial conditions, and all possible steps. It's really the entangled limit of everything that's computationally possible, the result of following all possible computational rules in all possible ways. Of course, this image can be just considered as a rough finite approximation of the Ruliology. The complete Ruliology encompasses the exploration of infinite limits across all conceivable rules, initial conditions, and steps, right? And also here, the nodes and edges are not really specific to any single entity. They can represent different entities, but just to give you an idea. And that's also a conceptual definition of the Ruliology, which I'm not gonna read for you. Please refer to the paper. We also define the Ruliology mathematically, computationally, with other things, if you'd like to read the computational and the mathematical definitions. So yeah, one of the most remarkable facts of the Ruliology is that it's really, in some sense, the ultimate necessary formal object. It's really, in some sense, a representation of all possible necessary truth, a formal object whose structure is an inevitable consequence of the very notion of formalization. And a very important claim about the Ruliology is that it's unique. Yes, it can be coordinatized and sampled in many different ways, but ultimately there's just one Ruliology. And then perhaps the most difficult issue is how to enumerate all possible rules. But here we can also use the principle of computational equivalence that tells us whatever basis we use, what comes out will eventually be effectively equivalent. And just also to show you an example, here are some Ruliology multi-way systems made with two color Turing machine. Here is some Ruliology multi-way system made from hypergraph rewriting systems. And also some Ruliology multi-way systems based on numbers. And of course, also these pictures can be thought of as a coarse finite approximations to the Ruliology. The full Ruliology involves, as we said, the infinite limits of all possible rules, all possible initial conditions, and all possible steps. And needless to say, this is very, very complicated thing to do. And I think since Xerxes did not have much time yesterday to tell you how to think about the Ruliology mathematically using higher category theory and homotopy type theory, I'll just briefly mention that. And as you know, the Wolfram model really provides sort of a computational realization of the Grothendieck's hypothesis. That is, Grothendieck's homotopy hypothesis states that infinity group points are spaces. And the question I mentioned before, that the first thing that one needs to answer if one wants to do physics in a background independent way is that where does space come from? What's the underlying structure of space? And one way to answer that, as I said, is through the rewriting systems. So actually mathematicians have been discussing that in the foundations for a very long time. And mathematicians think of spaces as decomposition of points. And then you can think of path between those points. And then you can think of path between path, and path between path between path, and so on. And there is some notion of building this infinite tower. And questions like these in part motivated the Grothendieck's hypothesis, which gives a recipe for showing how spatial structures emerge from an infinite tower of path between path. And the constructions in the Wolfram model actually provide a complete realization of this hypothesis. So just to show you something, of course, then interpreting the multi-way systems as types, the states of the multi-way systems as terms, and the rules as type constructors. Path are then proofs, homotopes between path, and proofs of proofs, and so on. And I'll show you just in a minute how we do that. So consider this multi-way string substitution system, right? And basically, what that says, every path in this multi-way evolution graph corresponds to a proof of a proposition. And in this particular case, we have a proof of the proposition that AA goes to A, BB, B, A, BB, right? That's start from AA, we go to that state, right? And basically, we can also have a different path that goes to the same proof, right? And that sort of illustrates the existence of multiple proofs of the proposition. And then a key feature of homotopy type theory is the ability to describe proofs of equivalences between proofs in terms of homotopies between paths. In this discrete setup of multi-way evolution graph, a complete realization of the homotopy map between paths can be given by simply introducing bidirectional edges, mapping vertices on one path to corresponding vertices on the other path and back again, as you can see here. And then you can just also keep going, right? And so in category theory interpretation, transformations between states in the original multi-way graph are like ordinary morphisms, one morphisms. But when we're making transformations between proof path, this is like two morphisms. And just as we can add transformations between proofs, we can also add transformations between proofs, and so on. And then the result, at the infinite limit, the continuum limit, we get the result. We can build up a whole hierarchy of higher and higher categories, eventually ending with an infinity category. And yeah, this is in a sense, I stole this from Sexy's presentation yesterday. In a sense, the Wolfram model provides a computational realization of pre-geometric structures in physics. And the mathematical framework of homotopy type theory provides the formal foundation of these structures. All right, so implications of the Ruliad and the central role of observer, right, which is the main thing of my talk today. So the Ruliad contains everything that's computationally possible. So why then do we have the perception that the universe has a specific laws and that definite things happen in it? The world seems to us the way it does because we are observers of the kind we are. But what ultimately is an observer, and how, for example, can we make a general model of one? As we now have general models like Turing machines for computational systems. In the past, it was usually possible to do theoretical science without really explicitly discussing the observer. Even in traditional physics, the observer has often been considered a passive entity, merely watching the universe. However, modern perspectives like quantum mechanics hint at the observer's active role in shaping outcomes. So actually, to say anything about what happens requires knowing about the observer. And it turns out that our limitations as observers are, in a sense, what give us many of the most fundamental scientific laws that we perceive. And a century ago, there were already some indications of importance of observers in physics, with coarse graining in statistical mechanics, choice of reference frames in general relativity, and measurement processes in quantum mechanics. But what we're calling observer theory is much more definite and formal, a coherent theory of observers that can be applied to let us derive conclusions in a whole range of different areas. In general, what an observer does is to take the raw complexity of the world and reduce it in such a way that conclusions can be made from it. And one can think of there being a certain fundamental duality between computation and observation, right? The process of computation has the effect of generating new outcomes, and the process of observation has the effect of reducing outcomes by equivalencing different ones together. So computation theory gives us a way to describe possible processes of computation. And the goal of what we're calling observer theory is to give us an analogous way to describe possible processes of observation. And again, so what an observer ultimately does is to take an input from a large set and return an output from a much smaller set. It's a concept that's really appeared in many fields under many different names. It can be called a contractive mapping, a reduction to canonical form, a classifier, a forgetful functor, lossy compression, projection, renormalization, group transformation, you name it, right? It's what's fundamentally going on whenever we use a sensor or a measuring device, or for that matter, our human senses. We extract statistics, fed to models, and describe things symbolically, say in human language. Thus, the observer, human or otherwise, acts as a kind of prism or a transducer, converting a potentially infinite spectrum of data into a finite package capable of being processed. And the prism is actually a good analogy because without it, there would be no such phenomenon. And just as a basic physical example, I mentioned here is that consider a gas pressure sensor based on a piston within the gas, right? And within the gas, molecules move around in a complicated and random ways, hitting the piston in all kinds of configuration. But the piston reduces out all those details, responding just to the aggregate force of the molecules, the same one of which can be realized in potentially infinitely many ways. And the main point is that what we can describe what's going on more formally by saying observations by the piston identify all different detailed configurations of molecules, preserving only information about their aggregate force, forgetting the finer details. And the same idea can then be given slightly different interpretations, right? Revealing how observers influence various or different branches of science. In statistical physics, for example, observers have, as just described, the effect of averaging over many particles or other degrees of freedoms. In general relativity, they are averaging over space-time regions and forgetting those details having to do with coordinate transformations. In quantum physics, they are basically averaging over many quantum histories. In mathematics, the same statements are stated differently in terms of the underlying axioms. And just to give you an intuitive explanation of a formal example of equivalencing, we can definitely, this can be given precisely in terms of coarse grading procedures in statistical mechanics. Specifically in classical statistical mechanics, the number of microstates for a given system is generally uncountably infinite, since the positions and momenta of particles generically take values in the real numbers. Therefore, in order to be able to define quantities such as the omega, namely the number of microstates that are consistent with a given macrostate within the Boltzmann entropy formula, it is necessary to constrain these microstates essentially by grouping them together into equivalence classes, thereby obtaining a countable set of states. In order to define such an equivalence class, one defines two particles I and j as being equivalent, which in this particular case means observationally observationally indifferent if the respective possessions and momenta are sufficiently nearby in value, as you can see in this matrix. And that shows the crucial feature of observers seems to be that the observer is always ultimately some kind of finite mind that takes all the complexity of the world and extracts from it just certain summary features that are relevant to the decisions it has to make. And observers like us have two basic characteristics. First, they are computationally bounded, and second, they are persistent in time. Computational boundedness is essentially the statement that the region of space observers occupy is limited, meaning that we can't expect to reverse engineer computationally reducible processes that are going on underneath. And in a sense, everything then becomes about the interplay between the computational irreducibility and our nature as computationally bounded observer. So the Wolfram model really takes the perspective that an observer has to be part of the underlying multi-way system, possibly as a subgraph spread across branches. And this view measurement is just the process of the observer conflating parallel threads of multi-way history with a single evolution, leading to the illusion of a unique sequential thread of time. Furthermore, the notion of causal invariance, which can be thought of as being associated with a path of history that diverge, eventually converging again, is what guarantees a coherent eventual consistency. You know, the Ruliology, as we said, it contains all possible rules, right? And since the Ruliology contains path corresponding to all possible rules, it's basically necessary that it will contain the inverse of these rules, that it will contain what's needed to undo whatever divergence occurs. And so because of causal invariance, the laws of physics are invariant in any reference frame, though to realize the laws one has to set up a system within a given reference frame. Hence, anything physically observable is going to be in a subjective setting. And from this subjective setting, when we infer anything objective, it's relative objectivism. And so any given observer is really interpreting what they see in terms of a description language, which causes them to attribute certain rules or laws to be the rules of the universe. And one has to choose what kind of a system one is working with, and it's almost impossible to state a law without those choices. Once we make those choices, we are already in a constructive domain. Hence, if one sets up some particular computational or mathematical theory, there will always be choices to be made. And our most important feature as observers is that we're computationally bounded. The way we parse the universe involves doing an amount of computation that's absolutely tiny compared to the computation going on in the universe. We really sample only a tiny part of what's going on underneath, and we aggregate the many details to get the summary that represents our perception of the universe. Recall our example of the molecules in a gas the molecules bounce around in a complicated pattern that depends on their detailed properties, but an observer like us doesn't trace this whole pattern. Instead, we only observe certain coarse-grained features like pressure and temperature. In this sense, everything then boils down to how an observer chooses samples the space in which they are located. And the different kind of observer sampling and parsing the system differently could in principle identify different features corresponding to different laws of physics. So what an observer is essentially just an equivalencing machine. And we will also describe in the paper in detail how the Wolfram framework can be interpreted or can be seen as a second-order cybernetic system. So yeah, the limits of Ruliology, the impossibility of seeing the Ruliad from the outside. Yeah, so Dean has added this lovely quote from Whitehead, which I also use it here. It's wonderful. It really summarizes this in a wonderful way. If philosophy, Whitehead says that philosophy is an attempt to express the infinity of the universe in terms of the limitations of the language. And if philosophy is just an attempt to express the infinity of the universe in terms of the limitations of the language, Ruliology is likewise an attempt to express that infinity in a somewhat less limited framework of the representations of computationally bounded observers that are embedded within it. The Wolfram model really depends on coarse graining over path in order to model the observed physics. The coarse graining is, of course, relationally linked to specific observers or classes of observers. This introduces a limit, since any periodic properties that we speak about are, of course, from the point of view of a member of such a class of observers. We can model other observers by changing the properties defining the observer class, but even this is itself generated from our own perspective and so will inherit any associated limitations. Of course, the Ruliad is also not something that we could ever directly observe, and nor it is presented as such. It is an abstract entity. However, in as much as it is abstract, it exists as a representation in the mind of an agent, and so it inherits the limitations. Along these lines, a complaint has been leveled against the Wolfram model is that it is incapable of making predictions, but that entirely misses the point, which is that the Ruliad is home to physical theories. It is the ground, and the fundamental theory cannot possibly be expected to make direct predictions of the sort that the critics clearly desire. But what it can do is to locate them in a web of theories, and moreover, it can suggest entirely new kinds of theory that would then themselves make predictions when properly worked out in the manner appropriate for less fundamental approaches. The task of physics indeed is to figure out where in the Ruliad we are located. Ruliology is not then a replacement of physics, but a way of making sense of it. What we have described is then not a theory of physics in the normal sense. It is a pre-physical framework for any possible theory of physics and should not be analyzed or critiqued in the same terms as orthodox physical theories. I think I'll just leave it at here. I'll just stop now, and if you have any questions, please feel free to ask them.
I'm not sure how good.
I can't hear anything, Dean, if you are speaking. I'm sorry about that.
I was going to say, I'm not sure the microphone is picking up, so maybe if you have a question,
Yes.
go and
No, I can.
speak into the actual microphone on the laptop there. David first, and Eric.
Can you hear me?
I can, a little bit.
A little bit. Shall I get even nearer? Where am I aiming for?
Yeah, okay, yeah, that's good. That's
Thanks very much for the talk. One question I had, so when you were showing us the rewriting schemes, I mean, something people were trying to do back in the day was right back here, was that rewriting schemes tend to come with a direction to them. They're sort of non-reversible, or they don't have to be reversible. So people were trying to set up a sort of directed algebraic topology to deal with this rewriting, and then even at a higher level between rewritings. I mean, there have been attempts to try and develop a directed homotopy type theory. Was there some reason you were looking particularly at reversibility here?
Well, not necessarily. We're actually trying to just come up with a structureless structure. We're not even. I'm not sure if would you consider this rewrite as a directed rewrite? If that's the case, it just came out as a coincidence. We're trying to really work with a structureless structure somehow, right? We're just trying to come up with the basic computational parameters, which is, again, as I described, as the archetypical underlying structure that is pattern matching substitution. Given a pattern, if it's matched, we'll transform it. We have also enumerated different rewrites, all kind of rewrites you could imagine. And definitely some rewrites are just very, very, very basic. And we could also show that simple rewrites can really lead to diverse and complex behaviors. So it's an interesting comment about the algebraic topology of rewriting. I'll definitely have to look into that. But I'm not sure if Xerxes also has something to add to that question, if he has an answer.
So does the Ruliology include all quantum computations or just classical?
Well, if you can think of, okay, let me show you something. I'm not sure if I can show it here. Okay, so one can think of a classical Turing machine as just a definite path in the Ruliology, right? You can also think of quantum Turing machine as all these different threads, but then the measurement is just really a process of conflating all these different threads to a classical thread, which really makes quantum computing very, very difficult. So yeah, of course it includes that. You can think of that in that way. Just it corresponds to different possible threads of history somehow. I guess I also do have some. Let's see if I have it in my presentation here, or I have to extract it from somewhere else. Yeah, so at the quantum level, there is a whole multi-way graph of possible sequences of updates that can occur, right? With each path corresponding to a different thread of time. And the crucial feature about us as observers that we don't perceive all those branching and merging threads of time. Instead, we imagine that we have a single definite thread of experience in which everything is sequentialized in time. And yeah, it's not really obvious that if we sequentialize time that we form any consistent view of the universe. But then again, there is the phenomenon of causal invariance. I can also show you a different. Just give me a second. I'll get it on the website. Just about the quantum computation and the Ruliology in general. Let me stop sharing and share that again. Should hopefully be very interesting. Okay, let's see. That's something that Stephen has written some time ago, and that's a Turing machine, just a normal Turing machine, and that's when we form Ruliology multi-theory graphs. And just wanted to show you that a definite path would correspond to a Turing machine, where just the path evolves to the next step based on a deterministic rule. And then you have a non-deterministic Turing machine, which also corresponds to a definite path, if I can find that. But you have a non-deterministic rule of just that tells you how the path evolves to the next state. And you have the quantum Turing machine, which just really corresponds to all possible threads of history. But then to make a measurement, you have to conflate all these, right? Which really is then the measurement problem. Might have been on a different thing, but I hope I can find it here. If not, I'll make sure to send you the link of, there you go. So this is a classical Turing machine, right? And this could also be a non-deterministic Turing machine. And basically, a quantum Turing machine just could correspond. You can think of it as corresponding to all these possible threads, right? But then again, to make a measurement, you have to conflate all these threads to a classical one, which makes it really, really difficult somehow. Not sure if that answers your question, but yeah.
I'm not sure. It seems to me that maybe I'm just not understanding what these graphs mean, but I'm kind of picturing the edges as containing bits. So making just non-deterministic doesn't make it a quantum computation. That you would have to
No, not
qubits.
necessarily. That's not the
is it
comment I made about.
representation of the quantum computation, or is it an actual quantum computation that's being represented by the graph? I mean,
It's not necessarily, this one is not necessarily a quantum computation. I just wanted to show you sort of a figure that tells you the idea, right? Okay, let's take a simple example. This is a multi-way Turing machine, right? A multi-way Turing machine, as I said, usually a classical Turing machine would have a rule that you keep applying to evolve the system. You would just get a definite path. So a multi-way Turing machine is definitely much bigger than an ordinary Turing machine. And so a Turing machine is a subset of the multi-way Turing machine, and thus would correspond to a definite path, right? Whether it is classical, deterministic or non-deterministic, that just tells you how the rule evolves to get to the next state. But a quantum Turing machine would correspond, if you want to think about that in this framework, would correspond to different threads. You could imagine just different threads that corresponds to the quantum computation threads in the Ruliology in this framework.
Right.
Does it make sense?
Yeah, but then you would be replacing the bits by qubits. Is that the idea? And having quantum computation on some of those qubits. You could just think of it that way.
I think I've written an argument about that somewhere. I'll try to find it and send it your way. It's exactly. I can't just find it now, and might take some time to actually look it up. I'll try to send it. Hello.
Hi there. Yeah. Can you help me with relating your way of thinking with physical reality? I mean a little bit in the orthodox way. Like everything that's described by physics as we know it, with current laws, etc. So should I think, my intuition would tell me, your gas and piston type of situation. If I look for somewhere in your multiverse there are tiny, extremely special situations. So so if I'm interested in, orthodox, old-fashioned physics, should I look for it in there, or are you thinking again of, some superposition of all of these things?
It's a wonderful question. Yeah, well, of course, a classical physical system should definitely be in there. Though it's also will not be.
Okay, quantum. Yeah, physics is quantum, of course. I would say. Yeah. Okay.
What the story of multi-way systems is how we really get quantum in these models, right? Because the quantum is really having different threads of histories, right? That can represent something. But it's really more about the pre-physical realism, not about the physical realism itself. It's more of how the interplay of the underlying computational irreducibility and us as computationally bounded observers, right? It's how we coarse-grain and come to conclusions about the things. So a classical system is definitely something that can be included. If you want me to share also
but should I look for a connection with physical reality, or you also said, well, predictions is really that's not the main point, right? This is what you said.
It's a representation, right? It just gives you an idea of how things work out together, and how you have the science that deals with constructing models that describe, or that hopefully provides useful descriptions. But here we're also not only trying to provide useful descriptions, but useful descriptions that include the observer in the description. Somehow it's sort of that makes it a more complete or a less incomplete description, right?
I'm not sure whether it presents added value unless I have some interpretation for this huge space of all possibilities. But it seems so huge, it's difficult to get a handle on it. So my only handle is, my intuition from orthodox physics. So if I then have the intuition, well, it's very sparse. I have to look very hard for it to find it in there. No amount of coarse graining over things that have nothing to do with orthodox physics will produce orthodox physics. So I'm a little bit lost in that huge space.
You?
That's fair enough, I guess.
That's good.
I mean, it's worth saying there are people working on this project who are trying to do exactly this and find analogies of general relativity, quantum mechanics. They're obviously in extremely early stages, and you can find easy to find problems with them. The way the correspondence between bits in the Ruliology atom constraint is linked to what we would not ordinarily think of as general relativity. But there are attempts to do that by Jonathan Gorard.
Well, I would say, of course, the devil is in the detail. Even with much simpler things, people, of course, look at this causal sets where that was named by several people as which is, I would say, is still kind of a tiny subset of all kind of oriented graphs with some decoration, which I think this can be thought of in a slightly intuitive way.
Yeah, you can even think of it in the way that Paul was talking about the other day with the solution space, right? There's a whole bunch of solutions, even in general relativity itself, that we think, no, these aren't the proper ones, and you need to sort of pin down your solution space, which maybe doesn't include CTCs and things like this.
I would say this is so vastly much larger that, the thing is, no amount of course grading will produce anything. I
also really have to say that some of the known of physics really appears as being highly generic features of this formalism, right? Especially the thing that we can think of that relates to, as you say, something physical is categorical quantum mechanics, which we just really showed that can be a subset of the more general multi-way system operator thing, right? And we also have there's some relativistic and gravitational properties of the Wolfram model that you can find online. ZX calculus is the thing that definitely relates to the closest physical thing. You can sort of reason about quantum circuits using this formalism. There's also connections to homotopy type theory, but I'm not sure that that's physical anymore. And of course, there are definitely work in progress on relating that to causal set theory and numerical general relativity and all of that. I'm not sure if that helps as well, but.
Okay, the question now. Okay, thanks, Hatem.
Thanks, everyone.
All right, I think we're a little bit early for lunch, but it might be there already. I can serve you some virtual lunch if you want over there, but I'm just going to say bye-bye.
Not allowed to eat anything, but thank you. Thank you.
I don't know whether, did anybody hear whether it has been served? Might be there already.
Yeah,
you get something with obviously the landscape, extreme landscape, especially with things like take lines.
The text was there as well.
Yeah, that's right. Interesting idea though. But if you've got his Ruliology is sort of a superset of everything. So everything's there. There's nothing wrong with it. It's a model of everything and everything has to be there, right? So I wonder how tautological
Yeah.
On the verge you have probably.
Things of interest.
Yeah.
It's asking too many. Asking too many.
Exactly. If it's a model of everything, then wouldn't you just expect everything to fall out?
It scales.
I don't know what often tells you you gain anything by doing it.
They drown out any,
Other than saying, well, this is the superset of all the things predicted. Everything has to be easy or anything like that. I don't know what to make of that.
Yeah, but if you want to get
And then you have to
so
think about
in
that.
most of these
The text of everything.
many states, there are
It must be points of pin. I mean, you can't even tell whether
that's
it's the same
the
or
more
not.
specific
That's
is what we call
it's not algorithmic,
so one has to
decidable
enumerate some of
sets of rules. They might be doing the same thing, but you don't know they are.
That's right. Yeah. And there's not even a sense of adjacency.
Yeah, right. What's the top
So
one?
every set to get rid of that.
Geometric structural things, yeah.
So the idea is, okay, then you are
This is the problem I have.
still
Read UKS.
you have some chance of like kind of superposing them or
Yeah.
coarse graining them, as you call it. You get something sensible.
Doorstop of the thing.
But
Right.
the set present fields or rules that it's so
He's got this idea that he keeps expanding this to infinity.
I understand, you know, the model of all, but the question is what's the added value?
Keeps expanding it.
From a physics point of view.
Forget from the exact point. It's so it could be physics. It's not physics. It's more of a physical
Physical world are the same kinds of
Which
patterns
is a
that merge
mathematical
out of
concept
this.
that is useful for some things, but
But it's such an artificial assumption, such an artificial
this
construction.
tension
It starts
between
with
the specific, right?
What it can do
And the
is,
general.
here's one thing you can do, is it can show you how the correlation
one
between
dimensional
kinds of measures that you make and versus
says rules about
and the kinds of you could expect to observe.
Only one dimensional.
There's not for single lines.
There's nothing there.
They also have one dimensional lines.
People were doing these stuff things, the gliders, all that stuff from, when was that?
Software is game of life.
Yeah, this is years ago, because it was like,
No, he, well,
Visual
in his
systems,
book, in case he wasn't doing that. What he was doing was saying, okay, let's have a single line of ones and zeros, and let's have all possible combinations of those, of all possible lengths or something, and then come up with all the possible rules for substitution you can have, and then iterate.
You could still say,
So
oh,
the iteration
it's not
then
time to this
generates
huge space of
complex patterns as you go. And complexity,
And
some
then
of them done, some go nothing, some just go mush.
Some
of them have
related to anything else.
self-reflective, self-singular. Yeah, exactly. You get self-singular Ruliology, and he somehow thinks that's significant. He thinks that's how the world is. But it's
So you have to specify.
I'm
But then it's the devil in the specification. How are you doing this?
tell us something about the world. I mean, I think the world is not right.
So general, so general.
So general.
Where's the world in all this?
Talking about observers,
It's interesting.
all possible
Design.
There's no cells, it's just rules and elements. You know, it's only you just say, you talk about it, so
But who knows?
easily identified.
No, yes, I'm just going to grab something.
Oh, wherever suits you. It's nice and cool in here, but on the other hand, it's nice and sunny outside.
Not too hot outside.
Well, it's better than it was yesterday. That's for sure.
Alright, I'll go and grab something.
Now I'm
This is a huge
extending my
About most representation of most mathematical structures, our knowledge is zero. So that's a problem. So only very specific, if you're talking about representation, only very specific structures I have well defined.
It makes sense.
But I just want to say, these,
Yes, but that was the whole point. I left it.
there's so many elements, it's not, you don't have the right intuition, also based on all of these objects.
In order to realize that well, if you really want to grow your research, follow your research,
Well,
don't
that's
stick to
fine,
one
mathematics is
technology
fine,
to be
but physics is about
try to become the world expert in that one thing and completely gone with the I learned much more after I just left my finished my so then I was more free to think. You're in BA and all this pressure to
quality,
only
that was
one
always
thing.
probably, it's very difficult to comment with zero mathematics because it's such a huge, unruly space. No, I just try to give you a hard time. It's a very,
Right now,
the space of the size of the
right now,
So the idea of using the logic of propositions.
See that? I'm only part-time. Yeah, I'm in a
Number of propositions.
I was in Barcelona until I was also teaching there. But then I
This is exactly exactly. It's the same problem. As soon as you start to go, think, how are the structures that we're using, mechanical structures,
And the rest of my time I
where are they
just do
coming
my own
from
research.
themselves? And you view that as a constructive.
Because even the research is not
And you're
wrong.
led into weird areas.
There is more like
You can't really
educational
help it.
things. So I kind of am using that like